Namaskara. In the previous session, we started our discussions on solving the min-max problem on an array of numbers. Let us assume that A is an array of n integers. You have to find the minimum of these n numbers and maximum of these n numbers. We have seen a direct divide and conquer algorithm, a naive application of the divide and conquer technique, and that algorithm had a complexity T of n given by T of floor n by 2 plus T of seal n by 2 plus 2 if n is greater than 1 and equal to 0 if n equal to 1. And this had a solution. T of n is 2n minus 2 for all n greater than or equal to 1. This is a solution of the recurrence equation. And when this recurrence equation, after solving the recurrence equation, we find that this is a very disappointing algorithm. We already have a 2-pass algorithm with the 2n minus 2 comparisons. So this is not giving any advantage. In fact, it is more complex with recursive calls and splitting and combining the solutions and other things. Whereas the 2-pass algorithm is a very simple one. Okay. So we are now trying to see whether I can use divide and conquer in a better way. Is there a way to improve the divide and conquer algorithm? One way is bottoming out at larger problems. Here the base case is 1. Recursion is when n is greater than 1. But we have observed that if you go all the way up to subproblem size 1, to solve a problem of size 2, you are doing a redundant comparison. You are comparing A and B again and again, which is not necessary, which means I can deal with the case when the problem size is 2 directly. Therefore, we will incorporate that as a base case. We will recurse only if n is greater than 2. So here is the pseudocode for that. Okay. Let us min max a 1 dot dot n, and it has got parameters. We are going to work on this array. All right, we can avoid this in specific array A. At various point you are going to work on a subarrays. So we will use the bound P and Q for specifying a subarray, and we have to output, we call that output as min and max. You are going to call this, suppose you want to solve the problem on an array B of size 2000. So you are going to call this as B1 2000 min max. Okay, you can call it as min B, max B, and so on. It's a very generic pseudocode. Min max A P Q. If P equal to Q, then there is only one element. That is a case of one element. So if P equals Q, then that is the minimum and that is the maximum. Okay. In this case, min equal to AP, max equal to AP, return min and max. This is the case when you have only one element. When you have one element, base case directly solved. No recursive call is needed. If n equal to 2, if number of elements is 2, so the next, if q equal to p plus 1, that means you have AP and AP plus 1, 2 elements are there. When 2 elements are there, in one comparison you are going to do that. Okay? If q equal to p plus 1, this is the case when you have only 2 elements. So, if q equal to p plus 1, compare. So, if AP is less than or equal to AQ, then min equal to AP, max equal to AQ, else min equal to AQ and max equal to AP, okay, and return min max. You can see that I am doing only one comparison. I am doing only one comparison here. So, these are the base cases. Otherwise, you are going to split. If neither p equal to q nor q equal to p plus 1, if this is not the case, then you come to the third one where the divide and conquer works. In this case, p and q are differing by more than 2, that means you are working on more than 2 elements. When you are working more than 2 elements, split. If you are working at 2, apply the base case. When you are working at 1, apply the base case. If it is more than 2, divide and conquer. So, what is that you would do? If q equal to else, you are going to have r equal to floor p plus q by 2, r is the middle value, and use the middle value to split. Okay, else r equal to p plus q, min max a p r min 1 max 1 min max a r plus 1 q min 2 max 2. So, the first half you find min 1 and max 1. In the second half you find min 2 max 2. So, you have found out through recursive calls. How will you find the overall min? Overall min is found by comparing min 1 and min 2, right. These two are these two are used to combine, these two are used to give min. These two are used to find max. This is the combining phase. You have recursively solved for the first half, you have recursively solved for the second half, then here is the combining one. If min 1 is less than or equal to min 2, then min equal to min 1, else min equal to min 2. So, you did one comparison and found the overall minimum. Similarly, if max 1 is greater than or equal to max 2, then max equal to max 1, else max equal to max 2. Overall min and max are now returned min and max. This completes the specification of the pseudocode. Okay? Our pseudocode specification is complete. We have addressed the base case, we have addressed the recursive call, and we have also indicated how the solutions returned by the recursive calls are used to find a solution for the given input. So, the recurrence equation is T of n equals T of floor n by 2, middle value is T of seal n by 2 plus 2 if n is greater than or equal to 3, and this is equal to 1 if n equal to 2, this is equal to 0 if n equal to 1. So, this is the new base case, this is the traditional base case, this is a new base case. So, I have a different recurrence equation. Now, I have a different recurrence equation. Contrast this, let me write down the first algorithm's recurrence equation, that is T of n equals T of floor n by 2 plus T of seal n by 2 plus 2 if n is greater than or equal to 2 and equal to 0 if n equal to 1. For this recurrence equation, T of n equal to 2n minus 2. What about this recurrence equation? What is the solution of this? Is it more efficient first of all, okay, or less efficient, or except for some values is it same? We need to solve this recurrence equation exactly like we did for this, right. We have to solve for this, but this is very tricky. Solving this recurrence equation, you can see that they resemble very closely, but solving calls for a lot of mathematical efforts, some detailed work we need to do. Okay? So, this is the beauty of mathematics. Two things may look very similar, but then when you look into the details, you need to attend a lot of mathematical work you may have to do. Okay? This is a case in that flavor. There is a minor difference, but the analysis is going to be a lot more difficult and detailed. So, let us take few values, right, and then see what is happening, and are we able to see a pattern or something like that to guide our analysis. Okay. So, T of n and T of n. If n equal to 1, T of n is 0. If n equal to 2, T of n is 1, because there are two base cases. And what about 3? 3 is T of 1 plus T of 2 plus 2. So, 0 plus 1 plus 2, which is 3. I am applying this equation. And T of 4. T of 4 is T of 2 plus T of 2 plus 2. 1 plus 1 plus 2, that will be 4. Okay. And what about 5? T of 5 is T of 5 is T of 2 plus T of 3 plus 2. T of 2 plus T of 3, 1 plus 3 is 4, 6. What about T of 6? T of 3 plus T of 3, right, in this equation. T of 3 plus T of 3 plus 2, 3 plus 3 plus 2, which is 8, 7, right. What is T of 7? it is T of 3 plus T of 4 plus 2. T of 3 plus T of 4, 3 plus 4 is 7, 7 plus 2 is 9. Okay? You can see that it is 9. What about 8? T of 4 plus T of 4 plus 2, 4 plus 4 plus 2, which is 10, and T of 9, 4 plus this is 12, and T of 10, T of 5 plus T of 5, 6 plus 6, 12 plus 2, which will be 14. Now you can see, are you seeing any pattern? This is T of n. Then we can write 11 and 12, 11. T of 5 plus T of 6 plus 2, this is 16, 12. 12 will be T of 6 plus T of 6, 8 plus 8, 16 plus 2, 18. Now 13 is T of 6 plus T of 7, 8 plus 9, 17 plus 2 is 19. Now you see, let us see the difference. The difference is 1 here, the difference is 2, the difference is 1 here, the difference is 2, 2, 1, 1, right. The difference is 2 here and 1 here, then the difference is 2, 2 and 1, 1. Now the difference here, it is going to be 2, 2, 2, 2 and 1. You are going to have 4 ones. You can see some values. So the differences are not always 2. There are certain differences which are less than 2. So when you add all the differences, that is what we are getting T, right. So for example, the differences are to be added to get T of n. T of n minus T of n minus 1 is D of n. T of n minus 1 minus T of n minus 2 is Dn minus 1. T of 2 minus T of equal to D2. Okay. Therefore, you have to add all of them. When you want to sum all of this, you get telescopic sum T of n, T of 1 is 0 is equal to sigma d I going from 2 to n. When all the differences were 2, it was simple, 2 plus 2 plus 2 plus 2 n minus 1 times. But here not all differences are 2. Some differences are 2 and some differences are 1. Okay. So it is a sum of lot of 2's and lot of 1's. Not all of them are 2. In the earlier case, the difference was always 2. Okay. So for this recurrence equation, the difference was always 2, but now the differences have a completely different pattern. All right. So let us determine the d values and use the d values to compute the sum. So if you look into the pattern d of 2, right, you forget it. For 3 and 4, it was 2 and 1. Then for 5, 6, 7, 8, it will be 2, 2, 1, 1. Then for 9, 10, 11, 12, it was 2, 2, 2, 2 each. And then 13 onward, 13, 14, 15, 16, this will be 1, 1, 1, 1. This is how it will be. We will prove it. So, what we have to see is that there are block of values defined by powers of 2. Okay. So, this is of the form 2 power k minus 1 plus 1 to 2 power k. When k equal to 2, so of course for 2 it is 1, for 1 it is 0. These are exceptions. Okay. Afterwards you see that 2 1, 2 2 1 1, this we will be able to. So, from 3 onwards I will be able to add based on this pattern. With that I will add 2, d of 2 is 1 anyway. Okay. So, this sum I write like this, this is equal to d2 plus sigma over block 2 sigma over block 3 B2 is 2 power 2, 2 power 1 minus, so 2 plus 1, 3 to 4. This is 2 power 3. Okay. Therefore, the kth block Bk defines 2 power k minus 1 plus 1 to 2 power k. Or I can change the notation slightly. I want to start from 1. So, let us we will define Bk like this. Sorry, I will change the Bk is 2 power k plus 1 to 2 power k plus 1. So, what is B1? 3 and 4. What is B2? 5 to 8. What is B3? It will be 9 to 16, right, 9, because B3 is 2 power 3 is 8 plus 1, 2 power 4 is 16. In general Bk is, so Bk has 2 power k numbers. From 2 power k plus 1 to 2 power k plus 1, Bk has 2 power k numbers. Half of them have difference 2, half of them have difference 1. That is what we have. The first half has difference 2, the second half has difference 1. So, we are going to split Bk into 2 parts. Two power k plus 1 to 2 power k plus 2 power k minus 1. This is, it has got 2 power k numbers. You split into 2 sets, each having 2 power k minus 1 numbers. So, 1 to 2 power k minus 1, that will have, the other half will have 2 power k plus 2 power k minus 1 plus 1 up to 2 power k plus 1. This is the second half. So, this has got 2 power k minus 1 numbers and this has got another 2 power k minus 1 numbers. So, Bk has 2 power k numbers. They are from 2 power k plus 1 to 2 power k plus 2 power k, which is 2 power k plus 1, and that is split into 2 halves of this interval. My claim is for all of them the difference is 2 and for all of this the difference is 1. For all of them the difference is 2 and okay. This is what we have to show. How do we show this? What we have as before is the following. D of n equal to D of ceil n by 2. D of n is ceil n by 2. Now, the difference is not always 2 in this case. Some differences are 2 and some differences are 1. Okay? It is equal to something smaller, but then there are 2 cases. So, if you look into D of 2 equal to 1 and D of 3 equal to 2. D of 2 equals 1. What is D of 2? D of 2 is T of 2 minus T of 1, that is equal to 1 minus 0, that is equal to 1. But what about D of 3? D of 3 is D of 3 is T of 3 minus T of 2, that is equal to 3 minus 1, that is equal to 2. So, they are different values. Therefore, from n to n by 2 when you go, you may reach 2 or you may reach 3. Depending on that, your D of n will be 1 or 2. It is not always 2. Okay? For example, let us consider D of 72. D of 72 is D of 36, which is D of 18, which is D of 9, that is equal to D of 5, and that is equal to D of 3, and D of 3 is 2. The moment you hit 3, you stop because D of 3 is 2. From 3 you do not proceed further. From 3 you do not proceed further because D of 3 is known. Do not apply again ceil and go to 2. Okay? But if you consider, let us say D of 107, that is equal to D of 54, that is equal to D of 27, that is equal to D of 14, that is equal to D of 7, that is equal to D of 4, that is equal to D of 2, that is equal to 1 because D of 2 is 1. So, if you start from 72, keep going by the formula n by 2, you land in 3. You start from 107, you land in 2. So, the process of replacing n by 2 may take you to 3 or may take you to 2. So, in Bk you have 2 power k plus 1 to 2 power k plus 2 power k minus 1. For all these n, the difference is 2. That means these guys should land in 3. An n here should take you to 3 and 2 power k plus 2 power k minus 1 plus 1 to 2 power k plus 1. If n is here, this process should take you to d of 2. That is the reason why it is 1, right. It is this n becomes smaller and smaller, like this 107 has become smaller and smaller and came to d of 2. So these numbers will become smaller and smaller, will become d of 2, and that will be 1. These numbers will become smaller and smaller and it will become d of 3, and that is equal to 2. That is the reason why first half is 2, the block value Bk consists of 2 power k plus 1 to 2 power k plus 2 power k minus 1. Another block is 2 power k plus 2 power k minus 1 plus 1 to 2 power k plus 1. All these things land in 3. All these things land in 2. By the process, d of n equal to d of ceil n by 2. Applying k times, you get this is equal to d of ceil n by 2 power k. Okay, applying t times, let us use t rather than k. Applying t times, you get this. At any stage, you are going to do this. So let us consider any number n in this range, 2 power k plus 1 less than or equal to n less than or equal to 2 power k plus 2 power k minus 1. You divide by 2 power k minus 1, you get 2 plus 2 power k minus 1 by 2 power k minus 1 is less than or equal to n by 2 power k minus 1 is less than or equal to 3. 2 power k minus 1 if you divide. Therefore, when you take ceil, this implies ceil n by 2 power k minus 1 equal to 3. That means this process after k minus 1 terms, d of n equal to d of ceil n by 2, which is equal to d of ceil n by 4. Finally, you are going to have d of 3, but I know d of 3 is 2. Therefore, all these guys will land in 3, therefore, the difference will be 2. The difference will be 2. For all these things, the difference will be 1, because after k minus 1 iteration, you are going to have 3 plus 1 by 2 power k minus 1 less than or equal to n by 2 power k minus 1 less than or equal to 4. Therefore, after k minus 1 iteration, ceil of n by 2 power k minus 1 equal to 4. Therefore, in this case, d of n equal to d of n by 2, it comes to d of 4, which is equal to d of 2, and d of 2 is 1. Okay? That means my block of numbers bk is defined by 2 power k plus 1 to 2 power k plus 2 power k minus 1. For all these guys, the difference will be 2. And for all these guys, 2 power k plus 2 power k minus 1 plus 1 to 2 power k plus 1. For all these things, the difference will be 1. we are going to see how we will use this fact to sum it and get a formula for T of n, because T of n is sum of all the differences. We know the structure of the difference in a block. We are going to use it for our calculation and analysis. I stop this session at this point, continue the analysis in the next session. Thank you.